Hello. Let's continue our LLM series. And in previous video, we talked about our inputs and how we convert our input or statement into input tokens. We talked about byte pair encoding. In this video, we will talk about attention weights. We will talk about attention score. We will talk about positional encoding. Why it is important and where we are going with this is the topic of this video. So let me take a real life example to make you understand this concept in a simpler way. So let's say if I say that we fought with each other and I got hurt. So in this statement, the context of this statement is that we had some sort of argument and we fought with each other, right? And I got hurt in that process. But if we complete this statement and if I just add one more thing, that he abused me, then I fought with each other, like then we fought with each other, and in that process I got hurt. The context of the first statement and the context of the second statement is totally different, because we have new information that the other person has abused or had said some nasty things to me, and that's why the fighting was taking place. So in LLM also, when we talk about anything, when we give input to our LLM, it makes a context matrix or context vector. It associates every word with a context vector. But how we know that, how to make that context vector, which word is more important with us in our input with respect to the words which we have given. Let's say I have given a word or a sentence that I am explaining LLM to you guys. So in this statement, which input or which token or which word is more important, in context of which word, is the whole idea of making a context vector or context matrix. So to get to our context matrix, we will go through the series of concepts. First of which is positional encoding. Second one will be your attention weights. Then third one will be our attention score, and after that we will go towards our context vector. So let's start from positional encoding. So I'm trying to make this video as simple as possible, and for people who are just interested and not from a STEM field, so there must be some details or keywords which are very basic to our STEM people from a STEM field, but I think I should also explain those words to people who are not from STEM field. So let me make this 2-3 words very clear for the people who are not from STEM field or from a science field, as we say in India. Is There are two types of properties, or how we measure things. One is scalar property and one is our dot property or vector properties, right? So let me give you an example to make it easy to understand. So let's say if I say the weight is of 10 kg or 10 pounds for a US audience or international audience, then we are just talking about the magnitude of that weight. Like it's a 10 kg weight or 10 pound weight. But if I say that I am accelerating my car in the direction of north with, let's say, 30 kilometer per hour or 30 mile per hour, then it's a vector property. So the difference between scalar and a vector property is that scalar property only has magnitude, 10 kgs, 10 pounds, but the vector quantities have a direction also associated with them, like acceleration in the direction of north, or let's say I have the current is flowing in the direction of south, so with some magnitude associated with that. So vector also has a magnitude plus direction. Why I explained vector to you is because we will use vector again and again while explaining the positional encoding. So that's the vector part of it. Okay, there is one more concept. Let's talk about, when we talk about higher dimensions, because our LLM functions in a very higher dimensions. But for simplicity of this video, I will keep it to the to three dimension only, x, y, and z. So to make you understand what is x, y, z dimension, so the video which you are watching right now is in 2D, because it has length and width to it. So it has x-axis and a y-axis to it. But when you watch a 3D movie in theaters and all, you feel something coming towards you. Like it has length and width, but something feels like something feels that it is popping out of screen towards you. Then that's your z-axis, which is third dimension. I hope that is clear. Like our 3D dimension or vector. Now, why I have explained vector in 3D dimension to you before I go on positional encoding is that when we take our input tokens, which we got by embedding or by doing byte pair encoding in our previous step, we say, let's take an example here also. Let's take an example of I am explaining you guys LLM, or I am explaining you guys about LLM or something like that, right? So let's take, if I take LLM as our token, for which I need a vector drawn towards it. Let's say this is an LLM token. From that statement, LLM is our token, which is let's say which will guide the vector, like it will give us the attention weight of every token associated to LLM. So if I take out that LLM token in our from our statement, as you can see on plot, then which another token in our statement is more important or have higher priority to make a context more clear is what we know as attention weight or attention score. Like which token I should give more attention to get the real context of LLM. That was wrong. So to get that context or attention weight, which token should I put more emphasis on to get the context of this statement with associated to LLM token is the score which we get is known as attention weight. I think I got misdirected in that statement. So keep it simple. We have a statement. I am trying to explain you guys LLM. LLM is, we picked out LLM as a token. So we got our LLM token. Then we go through the statement, we go through every token, like every word. Then we see, okay, which word in our statement is most important to get the context or to get the meaning of our statement, like you guys or LLM in associated to LLM. So if I plot this in a graph, you can see that the closest one would be guys or you, because that gives us the context of our this statement. So how we make our attention weights? So we go through every token or word, and we plot a vector to our LLM token here, like this, because we are plotting only three, because we are using 3 dimension space only. If you go in a higher dimension space, you will like plot more vectors towards LLM token, right? So let's take some different example. Let's say you start from a single step, right? So if I have to plot this, and if I take you start as our token, in associated to that token, I want to plot that vector with every token. Like you will have 3 vectors towards our start token. Then start from our sentence will have 3 vectors to our start token, and then so on and so forth. So you will get a grid of 3 3 3 3 3 3 score, like 0.1, 0.4, 0.8 is for you, 0.3, 0.8, 0.1 is for start, and so on and so forth. And I'm putting it as an example, and as I can see, like as I will put some graphic here to make this explain like more clearly. So that score which we got, like how close a token is with another token, is known as our attention score, or attention weight. So we get that attention weight. From there we will calculate our attention score, which I will explain you guys in the next video what is an attention score. And after getting the attention score, we go towards our context vector. So to get our context vector, we have to get the input tokens, we have to find a positional embedding. I'm let's say, again, if we take an example of, I am teaching you guys an LLM. So if I want context around LLM, so I will take LLM out and I will plot a vector for towards LLM for every token. So I will have, if I am using 3 dimension, will have three vectors pointing towards LLM. So I will have three different scores. Then you will have, I am teach M will have three vectors towards LLM. You will have three vectors towards LLM, and so on and so forth. And that score which we get, like how close the token is to another token, is known as attention vector. I hope I'm able to explain you guys that the attention weight and positional embedding. So yeah, in next video we will go towards attention score and context vector, and how we get our context vector. Because to get to our context vector, we make a different weight matrix, query matrix, and key matrix, and then from there we calculate our context vector, or we get our context matrix there. So yeah, I will see you guys in the next one. Till then, take care, peace, bye bye.